Welcome one and all to the third and final installment of Chapter 6. Today's lesson is really the key. If you completely understand today's lesson, you pretty much understand the other two, because today we're covering the general probability rules, meaning these rules work in any scenario. So you don't have to worry about is it disjoint or not, is it independent or not. These rules always work. Okay. I think I might have briefly mentioned Venn diagrams, but they do come in handy, especially as your problems get a little bit more tricky. So sometimes you're dealing with just two events. You would draw a Venn diagram, which is two circles, sometimes three, sometimes four, so on and so forth. So the Venn diagram helps you to see the various overlapping regions. All right, we mentioned this last time. If we have two disjoint events, then their union is simply the sum of their probabilities, right? Union means A or B. So if I wanted to find out, well, what's the chances of A or B happening, right? If they're disjoint, I can just say, oh, A plus B. That covers it, okay? But what does that mean, disjoint? Well, it means mutually exclusive. And here's a way of saying it mathematically. Events A and B are disjoint if and only if the probability of their intersection equals 0. So in other words, if they cannot happen together, there's no overlap. So, for example, let's say event A is drawing a heart from a deck of cards. Event B is drawing a spade from a deck of cards. When I draw one card, is it possible for me to get both a heart and a spade at the same time? No, right? Those are disjoint events. They cannot both happen at the same time. Okay? Give you another example. Let's say I roll a die. Event A is rolling an odd number. Event B is rolling the number 2. Again, those are disjoint. If I roll the die, I can't get an odd number and the number 2 at the same time. Okay? But let me give you an example where you have overlap. Okay? Event A, rolling an odd number. Event B, rolling a prime number. Now there's overlap, right? Now there's common elements to those two events. So that would be joint, okay? They would overlap. That's when I really want to draw a Venn diagram like this, and I can list what they have in common and be careful not to double count it, okay? That's the whole thing about joint problems. You have to be careful you don't double count the overlap. So let's try. Okay, so let's say I have two events and they have overlap. They have something in common, okay? So let's call this event over here A. We'll say this over here is event B. First of all, it's important to understand how to mathematically denote the different outcomes. If I'm in this circle over here, but only in A, then this circle would be considered A intersect B complement, okay? That's this section. Okay. If I'm in B but outside of A, well then that would be A complement intersect B. Okay, that's over here. And then this region right in the middle here, this is A intersect B. Okay, this is the area where both events occur together. That's the overlap, and that's what makes them joint. As soon as this has area, right? As soon as there's something that can happen where it fulfills both criteria, you have joint events. Okay, so now my question is, let's say I want to find the probability of A union B. Okay. There's a variety of ways you could do this, right? You could say, well, let's take this bit here, plus this, plus that. That works. That counts everything exactly once. So I could say, that's the probability of A intersect B complement, plus the probability of A intersect B, plus the probability of A complement intersect B. See, what I've done is I've broken up my Venn diagram into disjoint events and then just added them all together. Okay, that's always one way to do it. It's not the most common way, but it works. Okay, let's look at another way I could do it. I could take, how about if I take all of A, and then I would just have to add this bit over here. All right, that would work. Can you come up with another way to do it? Okay, pause the video for a sec, see if you can come up with another way. Okay. How about this? How about if I took all of B, and then I would just add this bit over here. That would also work, wouldn't it? Okay, again, the key thing is we want to calculate the area of this without any double counting. All right, now, I didn't give you the most common way to do it. The most common way to do it, oh, I did do that one. Here's the most common way to do it, right here. Okay, take all of A, take all of B, and then subtract the area that you've double counted. Okay, there's your most common way to calculate a union of two events. And you'll notice if this is 0, right, then you would have disjoint events and you'd have the formula that we went over last time. Okay, so this works whether it's joint or disjoint. And it's the most common way to do it. And because of that, it's right there on your formula sheet. So you don't have to memorize it. That's how you can calculate the union of any two events. Okay? So hopefully that makes sense. Okay, now what if I have 3 events and I want to find the union of 3 events? How could I do that? Okay, pause the video, take a sec, see if you could think of a way to do that. Okay, lots of ways you could do this, right? Actually, here's a great thing just to practice. I'd like you to label each and every one of these little individual sections so that you understand how the notation works. Okay, so let's do that. Again, pause the video if you need, label each section, and then we'll go over it. Okay, that would be this section here. I'm inside of A, but I'm outside of B and C. Okay. Over here, okay, I'm outside of A, I'm inside of B, and I'm outside of C. Okay, down here, okay, outside of A, outside of B, and inside of C. Okay. Now, this section here, notice I'm in A and B, but I'm outside of C. So this would be A intersect B intersect C complement. Remember, complement means it's not happening. right here, I would be outside of A, but I'm inside of B and C. So B and C happened, A did not happen. Okay. Over here, A and C happened, but B didn't. So this would be A intersect B complement intersect C. Okay. And then that leaves the middle overlap where all three events occur. So this is simply A intersect B intersect C. So there's all the different pieces of the puzzle. Oh, and by the way, I guess I should draw one more thing. There's no guarantee that all of them happen. It could be there's this bit outside here that is none of them happen. Okay. All right, so now the original question was, let's find the union of three events. So using your diagram, there's a lot of ways you could do this, right? Okay. We could take and add up each one of these little individual pieces, because the way I've labeled it, each of these pieces is now disjoint, right? So I could just add each one of those up. Or I might do this. I'm going to go for what I think is kind of the shortest way, because I don't have a lot of space over here. I could take all of A. Okay, so all of that. Then I would need this chunk here, so that would be A complement intersect B. All right, so I now have all of A, and I have this like Pac-Man here. So then all I have to do now is add that. And there you go. That would be one way to do it. Now, here's the catch. When you're doing these problems, you're probably not going to have infinite information. So you're going to have to be creative, and based on the information that the problem gives you, right, you're going to have to kind of break things up and make sure you count each section exactly once. So sometimes you could do this. Other times you won't have that information, right? Other times maybe you'll have all of B and then other pieces, or you'll have all of C and other pieces. Or I'll show you the most common way that this will end up being presented to you. It's kind of long. Okay. Typically what will happen is you'll have A, B, and C. So you'll start by saying, okay, I've got A, B, and C. Let's add them together. Now the problem with that is you've counted this red region twice, that red region twice, that red region twice, and that middle section you've counted 3 times. So you've overcounted quite a bit. So what happens next is you would subtract some stuff away, right? So you would typically be subtracting away this whole section here, okay? A intersect B. Okay, you've now counted that red section exactly once. You've still counted that twice, and that twice. So now you would probably end up subtracting away A intersect C, okay? Now you've counted that red section exactly once, and that once, and that once, but you've still counted this one twice. So you would then probably end up subtracting away that. Okay. So now you've counted all the red sections once. You've counted this once, and this once, but you've now counted the center section 0 times, so you'd have to add that back in. So that's a really long formula. There's no reason to memorize these formulas either. It's just common sense. So take the information that's given in the problem. You can't really control what's given in the problem, so there is no one right way to do every problem, right? Just count everything exactly once. So, draw the Venn diagram, put in the information that you have, and then add things up correctly, okay? So just be flexible. So that's what we just did. All right, that brings us to conditional probability. I think this is probably the hardest thing for students. Okay. We did a little bit of this when we did two-way tables. Okay. So conditional probability is when you have like a string of events happening. Like, I'm going to draw 2 cards from a deck of cards. What's the probability I get both of them hearts, right? So the first one's simple, 13 out of 52, but the second one is now depending on that first draw, right? It becomes dependent, and we call that conditional, right? So when I know something will have already occurred, what's the probability that the next thing happens, right? So that's the condition, and that's why it's dependent, okay? And here's how we do it, okay? So the probability of 2 events both occurring, right, A intersect B, is simply the probability of event A occurring multiplied by the probability of B occurring given that A has already occurred, right? So that's what this line right there means, given. Okay, so let's say that one more time. Probability of 2 events occurring is the probability of the first event occurring multiplied by the probability of the second event occurring given that the first event has already occurred. Okay? And you've done problems like this before. This is probably just new notation for you. Okay. Now, a lot of times, you'll actually be more interested in that, the conditional. What's the probability of B occurring given that A has already occurred? So, a little algebra, all you have to do is divide this original formula by the probability of A, and you have this. And the reason that I'm showing it to you this way is your formula sheet gives it, it gives you probability of A given B. So it's the same thing except the denominator is now B instead of A, right? Okay, so there you go. This is the formula you need for any conditional problem, okay? It works, but notice it will work for independent and dependent problems, right? It works for both. So just take this formula and solve it for whichever piece of the 3 that you're interested in finding. Okay. So that brings us to what I've been talking about, independent, dependent. Here's how we can now formally define independent events. Okay. So events are independent when the occurrence or non-occurrence of one event has no impact on the chances of another event occurring or not occurring. So, using our new notation, if the probability of B given A is equal to the probability of B, then A had no impact on B, right? A occurred, it didn't make a difference. B still has the same chance of occurring. So you could then say that B is independent of A, right? Because A had no impact on B's chances of occurring, okay? And we can go the other way around too, right? If the probability of A given B is equal to the probability of just A, then B had no effect, right? B didn't do anything to A, so we would say A is independent of B. Okay, so think of things like rolling 2 dice, right? Whatever the first die lands on doesn't impact what the second die lands on. Okay, flipping a coin and rolling a die. Again, whatever the coin lands on has no impact. Doesn't affect the chances of that second die landing on any given side. Okay. Drawing items with replacement, independent. Okay. Well, when do you get to dependent? Well, you get to dependent when you draw items without replacement, for example. Okay. So we mentioned this in last lesson. Last lesson we said if I have independent events, then their intersection is simply the product. Okay. So If these are equal, I have independent events. Okay. If they're not equal, then I have dependent events. It's that simple. There's actually obviously three ways to test independence, right? If the probability of B given A equals probability of B, then I have independence. If the probability of A given B is equal to the probability of A, I have independence. If the probability of A intersect B is equal to the probability of A times probability of B, I have independence, right? So there's really three different ways you could test for independence. So based on the information given in the problem, you could pick any one of the three to show independence. All right. Let's say I have three events. Here's how I could find the intersection of all three. Start by, well, I need the first event to occur. Take its probability. Then it gets multiplied by the probability of the second event occurring given the first has occurred, right? Then that gets multiplied by the probability that the third event occurs given the first two have occurred. So let me give you a quick example. Let's say I have a standard deck of cards and I'm going to draw 3 cards without replacement. Okay. So what's the probability I get, say, 3 aces? That'd be a nice hand in poker, right? If you only were playing 3-card poker, that'd be the best hand you could get. So here we go. The first card would have to be an ace, right? Well, what's the probability the first card is an ace? There's 4 aces out of 52 cards. So there's the probability of A in this scenario. Now, we're not putting the card back. So we now only have 51 cards left for our next selection. And how many aces do we have left? Only 3, because we took one of the aces out. So that would be probability of B given A. Okay. And now there's still one more card that needs to be an ace. Well, now there's only 2 aces left and there's only 50 cards left in the deck. So this would be how we would do the intersection of 3 events. So you can see how probabilities are changing, right? As we move down because we have dependence. All right. So let's try a problem. Cover that up. All right, so let's say your buddy Fred, he's applying to colleges, right? A lot of you are doing that. Good luck, by the way, getting into the college of your choice. So let's say Fred finds out the probability he gets into UCLA is 0.7, 70%. And his probability of getting into Duke is 60%, or 0.6. And the chances he gets into both schools is 40%. Here's the question. Are these events independent? Okay, so now there's 3 ways to test for independence. You have to use one of them. Okay, don't just say, oh, well, UCLA and Duke are different schools, so they must be independent. No, that's not how it works. Right? They might be looking for some criteria that's the same, or they might be looking for some criteria that's very different. So knowing that he got into UCLA might adjust your guess of whether he gets into Duke or not, and vice versa. Okay? It's not that the schools necessarily are talking to each other about Fred. It's simply, if you have that information, oh, he got into UCLA, would that change your guess on the chances of getting into Duke, and vice versa? Okay? So you have to test these mathematically. So let's see. Let's start with a Venn diagram. So let's call this one UCLA. Here's Duke. Okay, this is very nice. They gave me the probability of getting into both schools. So the intersection is 0.4. Okay. Now we know UCLA is 0.7, so that's the whole circle is 0.7, which means this section over here, this would be getting into UCLA, but getting rejected by Duke, is 0.3. Okay, and now Duke, I know the entire Duke circle is 0.6. So that means this section over here would have to be 0.2. That's getting into Duke, right? But not UCLA. Maybe I should have color-coded this. Okay, so you can now see the whole UCLA is 0.7, the whole Duke is 0.6, and the both is 0.4. Okay. All right. Actually, notice this doesn't add up to 1, does it? This only adds up to 0.9. So there's a section out here. There's a 10% chance Fred's going to be real sad, huh? 10% chance he doesn't get into either school. Poor Fred. Okay, now I've done everything. I can answer any question because I have a complete sample space written out in a Venn diagram. So, question A, are these events independent? I'm going to test it all 3 ways so you can see how any of the 3 ways would work. I'll start with the simplest test, the one I didn't even need a Venn diagram to do. So, if the probability of A intersect B, if that is equal to the probability of A times the probability of B, these will be independent. Well, they gave me A intersect B, it's 0.4. They gave me the probability of A. They gave me the probability of B. Question is, are those equal? They are not equal. Are they close? Sure, but that doesn't matter. They have to be exactly equal to have independence. So I conclude they are dependent events. Okay, so that's one way to do it. Let's use the other checks real quick. So how about the probability of B given A? Does that equal the probability of B? Okay. Well, the probability of B is 0.6. Okay. The probability of getting into Duke, given that UCLA has already said you're in. Okay. Well, that means I'm in. This is now my total area region. The condition is I've been accepted, or Fred has been accepted to UCLA. So the denominator of this is 0.7. I'm in here. That's the total area. And that's the area where B is occurring, given that I'm inside that circle. So the question is 4 sevenths equal to 0.6? It's not. 4 sevenths is close to 0.6, but it's not exactly 0.6. So again, this shows they're not independent. Okay, they're dependent. And let's do it the other way, just to, again, illustrate, because you have to know how to do it depending on what's given. Sometimes you don't have all the information. So probability of A given B, does that equal the probability of A? Okay, so if Fred is accepted at Duke, knowing that information, would that change the chances of getting into UCLA? Well, getting into UCLA, we know that that's 0.7. Okay. Now, we're given that Fred's been accepted to Duke. So we're in this circle. This circle has a total area of 0.6, and 0.4 of that would fulfill the criteria of getting into UCLA as well. Now, does 4/6 equal 0.7? No, 4/6 equals, that's 2/3, right? So these, again, not equal. So those are the 3 ways to test for independence. Now, do you have to do all 3? No, right? If you fail one, you will fail all 3. If you pass one, you will pass all 3. So you really only have to do one. But as always, it's a good idea if you have the information to check it more than one way, because that's how you can catch a mistake. Okay. Oh, what's the probability he's rejected by both? 0.1. We actually already did that problem right there. 0.1. Okay. So these Venn diagram problems are really just kind of about subtraction, really. And then to get your conditional probabilities, you're going to be dividing segments of one circle divided by an entire circle. Okay? All right, that brings us to Beige Rule. I do not have Beige Rule memorized. Beige Rule is not on your formula sheet. If you want to use it, then you will have to memorize it. But guess what? I can do every Beige Rule problem without having this rule memorized. Really interesting story about Bay, by the way. You can look him up. He was I forget if he was a priest or a monk. But long ago, he did a whole bunch of work on probability, but he never published it because the church back at that point in history saw it as heresy. So he had worked out this and other things dealing with probability, but never told a soul. And then people found his work after his death, and eventually he did get credited for his work. So that's kind of cool. Anyway, here's Beige Rule. I'm not even going to read it. If you want to memorize it, go ahead. Let's do a problem. And once you see how to do a problem using Beige Rule without memorizing the formula, hopefully you won't need to memorize the formula. Okay? So here we go. I got the answer written there. Sorry. All right, so I'm a hypochondriac. Not really, just pretending. And let's say I read about a rare disease. 1% of the population has this disease. So, of course, being a hypochondriac, I have to run out and get tested, right? Now, it turns out the test is 98% accurate if the person actually has the disease. Okay. Now, if I run out and get tested and I don't have the disease, there's a false positive 5% of the time. Okay, so I run out there, I get tested, I test positive. Oh no. What's the chance I actually have the disease, right? Because it could be that I landed in that false positive region, okay? All right, so there's a variety of ways to do it. I think I'm gonna use a tree diagram here, okay? Just so you can see a tree diagram at work. So here we go. All right, here I am. I'm really sad because I'm a hypochondriac. Now, it could be that I actually do have the disease, and it could be that I actually do not have the disease. I have to fall into one of those categories, right? So, has the disease, does not. Lovely dogs again. Okay, now, turns out only 1% of the population has the disease. Okay. Now, if you have the disease, and you take the test, it can be positive, which would be a correct result, or it could be negative, right? That happens sometimes, a false negative. Okay, if I don't have the disease, again, there's two outcomes. I could test positive, I could test negative, okay? So again, correct result, incorrect result, but those things happen. Okay, so now I have to put my probabilities in here. So 1% of the population has the disease. %99 of the population doesn't. Now, if you have the disease, 98% accurate that I will test positive, which means 2% of the time you would test negative. Okay, over here, if I don't have the disease, 5% of the time I would test positive even though I don't have it. And 95% of the time I would test negative. Okay. Now, it turns out I test positive for the disease, which means I must be here or here. Okay, so this right here, this branch would be 0.01, it's 0.98. Okay. This branch here is 0.99, it's 0.05. Okay, I'm definitely in one of those two branches because I tested positive. Okay, so the sum of those two branches is the denominator. Now, of course, the numerator would be, I actually have it, so that's this one. So my answer will simply be 0.01 times 0.98 divided by 0.01 times 0.98 plus 0.99 times 0.05. There you go. So I used the tree diagram. There's 4 outcomes in the sample space. Then I looked at the condition. I tested positive. So now there's only 2 possible outcomes in the sample space because I tested positive, right? So that goes to the denominator. Those are the, got to be there or there. And then the numerator is the condition that I'm actually interested in. So there you go. Work it out. And hey, look, only a 16.5% chance that I actually have the disease, even though I tested positive for it. So that's always a side note. Anytime you test positive for a disease, go back and figure out, could this be a false positive? Okay. All right, here's a fun problem. Let's try this one. Oh, and by the way, we just did Beige Rule. We just didn't write down any formulas. We used common sense. All right, here we go. Events A and B are independent. They tell me the probability of B complement. They tell me the probability of A union B. They want me to find the probability of A. Pause the video, give it a try. Warning, a lot of students miss it, so give it a shot. Think logically, see if you can do it. Okay, so it told me B complement is 0.6, so I know that B must be 0.4, right? That's the definition of complement. And they told me the probability of A union B. And they want me to find the probability of A. Now, a lot of students just go, oh, let's subtract these, but that's only if they're disjoint. The problem doesn't say disjoint. The problem says independent. Okay, and that's a common thing. Students confuse independent and disjoint. Please don't confuse them. They're different. They're different words for a reason. They have different meanings. Okay, disjoint means no overlap. They cannot happen together. Independent events kind of have to be able to happen together because when one happens, it can't affect the chances of the other happening, right? So if events are independent, they can't be disjoint, right? If they're disjoint, event A happens, now event B's probability of happening is 0 because it can't happen together, okay? So they are different words. Make sure you understand their meanings. All right, so here's how I would do it. I'm going to start with, I know A union B is equal to the probability of A plus the probability of B, minus, okay, minus the intersection. Okay. Now I'm going to fill in the information I know. I know that A union B is 0.7, 70%. I don't know A. I know that B is 0.4. And now here's where that other piece of information comes into play. It says A and B are independent. So that must be equal to the probability of A times the probability of B. Now I'm able to do that because the problem specified they were independent events. Now, again, I know the probability of B. Probability of B is 0.4. And now it's just an algebra problem. Okay, so subtract the 0.4. These are like terms, right? This is 1 times the probability of A minus 0.4 times the probability of A. So 1 minus 0.4 is 0.6. Right? Just pretend that said X and X, right? Just algebra. And divide. So the probability of A is 1/2 or 0.5. Okay, notice that is not the same as 0.7 minus 0.4 because 0.7 minus 0.4 means disjoint, does not mean independent. Okay, that was fun. All right, let's look at some more problems. Let's look at, there's a lot of problems about drawing things, so here's an example of that. So let's say there are 5 blue and 4 white marbles in a jar. Fun game, right? Marbles in a jar. Now you're going to play a game. 3 marbles are going to be chosen without looking and without replacing them. And if exactly 2 of the marbles that are chosen are blue, you win $1 million. Hey, now it's a pretty fun game, isn't it? So what's the probability of winning that $1 million? Okay. Now, you could use a tree diagram. You could use an entire sample space, right? You could do a lot of different things on this problem. So pause the video, give it a shot. Okay. Maybe I'll do a tree diagram. Well, I already did one of those. I'll do it anyway. So here we go. Three marbles are chosen, yeah. So first, second, third. Okay, so this is everything that could happen. I could get 3 blues, 2 blues followed by a white, so on and so forth. That represents everything that can happen. Now I just have to fill in, well actually before I fill in everything, why don't I look at the outcomes I'm interested in? I'm interested in exactly 2 being blue. Okay, so blue, blue, white, I'm interested in that one. Blue, white, blue, that's a good one, that would win. Nope, that's a loss. White, blue, blue works. And the rest would not win, right? Those are the 3 outcomes in my sample space where I have exactly 2 blue marbles. So now let's fill in the branches. Okay, our first marble chosen, there's a 5/9 chance of being blue and a 4/9 chance of being white. Okay, now here's where the conditional comes in, right? I've removed up this way, I've removed a blue marble, so there's now only 8 marbles left. 4 of them would be blue, 4 of them would be white. Okay, continuing down the branch here, I've gone blue, blue. There are now 7 marbles left, and 4 of them are white. Okay, if you want, you can throw this one in. We don't need that branch, but you could write that in if you care. Okay, here, blue then white, so there are actually 4 blues still left out of 7 marbles. Okay, and here this would be 3/7. Okay, going this way, I've removed a white marble first, so I still have all 5 blue marbles left, so that's 5/8, that's 3/8. Going to the next branch, well, now I've removed 1 of each. Again, 7 marbles left, 4 blue, 3 white. Okay. Down here, I've removed 2 white marbles, 7 marbles left. All 5 blues are still left, and only 2 of the whites are left. So I actually did the whole thing just for fun, even though I'm really only interested in the sum of those starred values. Okay, so we've got 5/9 times 4/8 times 4/7. That's for this branch here. Okay, this branch here I've got 5/9 times 4/8 times 4/7. Interesting. Down here, okay, this one looks different at first at least. So down here, That one is, put arrows, 4/9 times 5/8 times 4/7. Wait a minute. Those are all equal, right? The numerators for all of those, 5 times 4 squared. Denominators for all of those, 9 times 8 times 7. They're all equal. Okay. And you can also see 9 times 8 times 7. Hey, that's kind of like part of a factorial, right? Hopefully you remember factorials. Well, you may not have. You probably learned them in like math 1 or 2 maybe. So anyway, I can do this anytime I want, or I could just do 1 and then times it by 3. That's another way to do it. Or even better yet, you could use combinations. Remember those combinations? Yeah. So here's how I would do it. I might do it this way for fun and as a check, but if I were in a hurry and I wanted to do this quickly, I would say there are 5 blue marbles and I want exactly 2, right? So that would be, depending on you, I'm not sure how you wrote this when you first learned it. You could write it like that, 5C2. You might write it like this, right? I've seen that. And you might also see it like this. Okay, so I'm not sure what notation you're familiar with, but 5, choose 2. That's for the blue marbles. For the white, you need 1 white marble because you are selecting 3 marbles in total. So 4 white, choose 1 of them. Whoops. Okay. So that's the number of ways that you can fulfill the desired outcome. Now, of course, you're going to have to divide that by 9 marbles, choose 3. So just ignore that other bit there. There's your answer. Quick and easy. You might be interested, hey, how do I find this on my calculator? Well, no problem. Go into your math menu, scroll on over, and there it is. Permutations and combinations. So I wrote it this way because that's the way it appears on your calculator. Right? I think what I actually have to do, hold on, is put in the 5 first. So 5. Choose 2. Hey, that's 10. Write it over here, 10. Okay, and then 4, choose 1. Hopefully you realize that's 4, right? But I'll show it to you on the calculator. Whoops, I forgot the 4, didn't I? Right, that's 4, because if there's 4 items and I'm going to take 1 of them, there's 4 ways that can happen. That's what we're saying. Okay, and then my denominator is 9, choose 3. So there's my answer, 40 out of 84. Okay. So let's multiply these out. Let's see, that's 20, that's 80. Right, so adding those up, that would give me 80 plus 80 plus 80, 240 out of 504. And I'm claiming that that will equal 40 out of 84. Okay, so you can see the combinations are very useful when you are doing conditional probability, right? Remember, combinations, order doesn't matter, and there's no replacement occurring. That's when you get to use these combinations to make your life easier, okay? Permutations, order matters, right? So that's when you would use a permutation, okay? And if there is replacement, well, then you don't have to worry about conditional, right? The probability just stays the same every time. Okay, moving on. Some card questions. All right, so let's say you are playing cards, 5-card poker. What's the chances you sit down and you're dealt 4 of a kind? Wow, that'd be a good hand for 5-card poker, right? Well, again, I would use combinations to do this. Okay. So let's say, oh, I don't know, I want 4 of a kind aces. Okay. I want them to all be aces. So there's 4 aces. I need to choose all 4. Again, I'm getting 5 cards though, so that means I have to get 1 non-ace. There are 48 non-aces, and I need 1 of them. Okay, and I'm going to divide that by 52 cards, and I'm taking 5 of them. Right, that plus that has to equal that. Right, and it also has to equal that always. All right, so that's the probability of getting 4 aces. That'd be a great hand. Okay. Now, it didn't specify just aces, right? 4 of a kind for anything. Well, there's 13 different 4 of a kinds, right? Aces, kings, queens, jacks, 10s, 9s, and so on and so forth. So I would just multiply this by 13. Or you could say 13 4 of a kinds. I want to choose 1 of them. And there you go. That's how you can find the probability of being dealt 4 of a kind if you receive only 5 cards. It's pretty darn small. And that's why it's a very powerful hand, right? The lower the probability, the stronger the hand in poker. Okay, let's try one more. What's the probability you're dealt a flush if you receive 5 cards? Okay, here it's actually not, I mean, combinations are fine, no problem, but you could do this without combinations pretty easily as well. Whereas the other ones, it's a little harder to do without the combinations because I'm not needing all 5 cards to match, right? I'm actually needing 1 card that doesn't match. But with a flush, all 5 cards have to be the same suit, okay? So doing combinations here, pick any one suit. Let's say I want a flush in, I don't know, spades. So I want 5 spades. Okay, well, there are 13 spades. I need 5 of them. There are 52 cards. I'm taking 5 of them. Okay, but now there's more than 1 suit that would create a flush. There are 4 suits, and I need 1 of them. So there you go. That's the probability of being dealt a flush if you receive 5 cards. But again, I said you could do this very easily without combinations. You could say the first card, it could be anything in the world. Okay. Now the second card has to match the same suit as the first, so there would only be 12 left in that suit. And then the third card has to match the 4th card and the 5th card. So that's not using any, combinations to get there. Okay. These are equivalent. Fun stuff, right? But you can see the probability of a flush is much higher than the probability of 4 of a kind. And that's why 4 of a kind beats the flush. Okay. Now, just for fun, because we ran pretty long here, here's a bunch more 5-card poker hands. Feel free to try calculating those on your own and check your work. Okay. But you can see this is the ranking of hands in poker, right? That's why royal flush is the best hand. Very, very, very unlikely. Okay. Straight flush is very good. I've never lost with a straight flush. I've never even had a royal flush, by the way. 4 of a kind, full house. Full house is a 3 of a kind and a pair. Flush is all the cards are the same suit. Straight, 5 cards in a row. Doesn't matter the suits. Okay, 3 of a kind, 2 pair, and a single pair. So you can see with a single pair, not that great of a hand, right? You really want to get further down the line here to feel real confident in having a winning hand. Okay, hopefully that is fun. Feel free to calculate probabilities of any game of chance that you enjoy playing and use it to your advantage. All right, guys, enjoy.